Okay, so in my previous class, I talked about the basic definition of ring. Then I talked about few examples and then few terms related to rings. For example, I talked about subring. Then I talked about ideal. So in ideal, we have already witnessed two different kinds, left ideal and right ideal. And we have seen that if in some of the rings there exists some left ideal which is not a right ideal, and in some ring there exists some ideals which are right ideal but not a left ideal. And certainly in case of a commutative ring, if we have left ideal, then we can also think of that as a right ideal as well. So we have seen few of these examples. Along with that, we also heard about the term integral domain. Integral domain. And to understand that, we had the term zero divisor. So all these things we have already dealt with, and hopefully in your undergraduate course also you studied all those things. Maybe for few of you may not heard about, or you may not dealt with much of ideals. Okay, but believe me, in ring theory, ideal plays an important role. So in this class, I will again deal with little bit more properties of ideals, and then we'll deal with quotient of a ring by the ideal, and then we talk about few of these important questions that are usually asked in competitive exams. So that will be the basic idea of today's class. Okay, so when we talk about ideal, so as I mentioned in my last class, that in case of group, we have the idea of normal subgroup. So normal subgroup. In case of a ring, the similar idea which actually helps us for quotient in case of group, the similar concept present here is known as ideal. So as we remember, in case of a group, if G is a group and H is a normal subgroup, then we can have this idea of quotient. That means all such elements of this form G plus H such that G belongs to G. So that's the basic idea of our quotient. Similarly, here also, if we have R as a ring and I is an ideal, then we could have R quotient I. So as we remember, or if we go back, then you might have seen that if H is any subset of G, say if H is any subset of G, may not be a subgroup or may not be a normal subgroup, then also we can define this. So this is always defined even if H is not a normal subgroup. But for algebraists, they are not happy with only a set. So this is just a set. But to have some group structure, H has to be a normal subgroup. So unless H is a normal subgroup of G, you cannot have G quotient H to be a group. So you cannot impose some of the group structure on G quotient H. Similarly, in case of ideal as well, if I is an ideal, then R quotient I, you can impose some of the ring structure on it. So the question is how? Suppose R plus dot, say R plus dot is a ring and I is an ideal. So I am now trying to construct R quotient I. So the elements looks like this, such that R belongs to R. Okay, or I can write it like with respect to multiplication. So it's basically R quotient I. It depends. So I could have two different types of things. Uh, Either it could be written in terms of like Ri, or maybe of this form R into I. So let me first try to explain what does it mean. For example, if I have Z and if I have say 4Z, Now if I consider this R quotient 4z, then how it looks like? So it means that you just, so Z plus is a additive group and says Z plus dot is a subring, or Z plus dot is a ring and 4z plus dot is a subring. So how this group looks like? So this groups looks like, so you have all integers n plus 4z such that n belongs to z. See, if I write like this, so here R comes from the original ring. So here n comes from the original ring, and then plus 4z. So here I was my ideal. As we know that 4z is also an ideal of z plus dot. So here n plus is nothing but n plus 4z. So you can see that n plus 4z, how this n plus 4z looks like. So if you see here the detailed structure of n plus 4z, how it looks like. So n plus 4z, so this is one element and the collection of all such element. Now just have a look at how this one element looks like. So this is nothing but you have n plus 4k such that k belongs to z. That means this one element actually stands for a set. How? So this is n added with all the elements of 4z. That means each of these elements looks like n plus 4k. That means just adding all integers and then adding n with all multiples of 4z. I mean multiple of 4, right? So this is nothing but a set, and you can understand that if you keep on doing this sets, how many elements are there or how these elements look like. Okay, so here we have basically uh, elements are of this form. So how many different types of elements you can see? So n plus 4z, it may be 0 plus 4z, it may be 1 plus 4z, it may be 2 plus 4z, it may be 3 plus 4z, and it may be 4 plus 4z. Now just have a look at what would be the difference between 0 plus 4z and 4 plus 4z. Now if you consider the set, so here we are varying like this. So we are varying like this. So here n is fixed. So for this element n is fixed and k here varying. Okay, so we are considering 0 plus 4z and 4 plus 4z. So this part is the collection of all integers which are multiple of 4, and you are basically adding 0 with all multiple of 4s. So that will simply looks like as a set 4z. Now what's about this? So you have all multiples of 4 and just you are adding with all the multiples of 4, you are adding each of these elements with 4. Then what it will look like? Can somebody will tell me how this 4 plus 4z will look like as a set? It will simply look like what set? Anybody? Yes, so it should be same as 4z. So these two elements are the same. So 0 plus 4z and 4 plus 4z are the same. Similarly, 1 plus 4z and 5 plus 4z, they are also the same. Similarly, if we have 9 plus 4z, that will also be the same. So in a nutshell, we can say a very important observation that if a plus I and b plus I are two elements of this R quotient I, then they are equal if and only if, that is very, very important result, if and only if A minus B belongs to I. This is very important result. Now, if instead of plus, if I have AI, that means if this is with respect to multiplication equal to B with respect to multiplication, if these two elements are same, if and only if A into B inverse belongs to I. So these two properties are very important, and I'm sure in your undergraduate studies you might have or you must have dealt with all those things in case of group. So I'm still now I'm not considering with say anything beyond the idea of group. So if you have this idea or if you already done it in case of group, then you are basically you have this basic idea. So if you forget it or if you have not dealt with this kind of idea, I request you to just go through your undergraduate any book or any of the books that I am referring here, Damit Food or my book, Adhikari or Malik Sen Moderation, any of this book, you will get all the detailed idea about your uh, whole concept. Okay. Now, I will come to uh, first very interesting idea, like what is the idea of this quotient? So Z and the ideal 4Z. So we have taken an quotient. So Z quotient 4Z, right? Now, is there any advantage of this? Let us try to have a look at this. So that part we have already seen. So when I will talk about you regarding this isomorphism, homomorphism, etc., then you will find that this is isomorphic to Z4 plus dot. So this part, I think the teacher Arnav, he is teaching you this group part. So I will tell him to explain the homomorphism part. There is no point that both of us will teach the same thing, the homomorphism part. For group homomorphism and for ring homomorphism, the idea is exactly the same. In group, you have only one operation. In ring, you have two operations. So the same property will hold here also in case of uh, two, or even if you have more algebraic structures, then it will also preserve the more algebraic structures. So for group isomorphism, almost the same concept extended in case of ring. So I'm not going to details of that, but so I will request you to just have a look at the homomorphism for groups. That will be sufficient for me. I will extra thing I will do. Okay, but let us try to have a concept, like suppose I have a ring R3 plus dot. So as you know, what does it mean? The whole three-dimensional real vector space. So we can think geometrically as like this. So suppose this is X, this is Y, and say this is Z. So any point here looks like ABC. Okay. So this is my XY plane. Okay. So this is my XY plane. So, so this is my ring. First, tell me question one, let I equal to all the elements from XY plane. That means if the value of this Z is 0, basically if the value of Z is 0, then I will be in the XY plane. That means this belongs to R3 if I consider this. So the representation of XY plane I can write like this: X comma Y comma 0 belongs to R3. First, my question is, let this is I an ideal of R3? First question. So R3 plus dot is a ring. My first question is I an ideal of R3? What will be your answer? Please somebody tell me what will be your answer. Yes or no?
Yes.
Yes. So how to check this? So first of all, I is a non-empty set because 0, 0, 0 belongs to I. Now, if you take any 2 points here, any 2 points, that means let x1, x2, 0 and y1, y2, 0 belongs to I, then if you just subtract them, then x1, x2, 0 minus y1, y2, 0, that is of this form x1 minus y1, x2 minus y2, 0. So that is also in this form because the third coordinate is within is 0 and both of them they are in R. Also, to check whether this is, we need to check any point from R3. So let ABC belongs to R3. Then to check whether it's a left ideal, we need to put ABC into the point x1, x2, 0. As I mentioned, so this is an ideal with respect to the usual addition and multiplication of R3, right? So it is with usual addition and multiplication. So I will come to it just after a few sentences. That means if I have usual multiplication, so x1, bx2 and then 0, that is also in I. So this is a commutative ring. So we can say that checking from the left is sufficient. So this is a left ideal and hence since this is a commutative ring, this is also a right ideal. So as a result, we can say that I is an ideal of R3. Is it clear to all of you whether I is an ideal of R3 or not? Okay, good. Now the question is, question number 2. Okay, maybe I can write it here. Question number 2. What is R3 quotient I? So as I mentioned, I is an ideal, so you can very much do R3 quotient I. So my question is, what is R3 quotient I? So this is and what would be the geometrical representation of this? So this is an ideal. We have already proved R3 is a ring. So this is very much well represented. Now my simple question is, what is R3 quotient I? What is the geometrical representation of R3 quotient I? Or if I break it like this, what is the geometrical interpretation? What is the geometrical interpretation of an element of this quotient ring? Okay, so I assume that you understand what is the meaning of this quotient ring. So is anybody is there who is not acquainted with this quotient structure? Similar structure as this. So maybe I'll just explain for them a bit what is this structure, how it looks like R is a ring and R quotient I. As I mentioned earlier, the elements looks like this, right? So R belongs to R. So this is a set and I is an ideal. So this is collection of some elements. I need to show R quotient I is a ring. So need to show R quotient I is a ring with respect to some operation, say star and dot. Okay, so first let R be the ring with simple plus and dot. Now I need to define how this star and how this dot is defined. Okay, so first I need to do this star. So two elements, say R1 plus I is an element and say this is star R2 plus I simply define R1 plus R2 plus I. Now tell me, this plus is from where? This plus, note that this plus is from here. This plus is from here, the same plus, and this plus are the same, because this is each element of I will be added with R1 plus R2. Here, this plus means each element of I will be added with R2 and so on. Similarly, if I have R1 plus I with respect to this dot, then R2 plus I, how it should look like? It should look like R1 dot R2 plus I. So what is this R1 dot R2? And this dot is nothing but the ring dot. So now with respect to this star and this big dot, we can show that if this is true for all R1 plus I, R2 plus I belongs to R quotient I, then it's very easy to show that with respect to the star and dot, R quotient I star and dot, this big dot forms a ring, and this ring is called quotient ring. Just like same concept as when we dealt with normal subgroup in case of a group, the same concept. Unless you have the normal subgroup or the ideal concept here, you cannot have some algebraic structure on R quotient I. That's why it's essential to have this. Okay. Now come to my this question. What is how this each element geometrical interpretation of an element of the quotient ring? Okay, now I request some of you please try to understand or try to explain how it looks like. So is the question clear? I'll write it more clearly. Maybe I have R3, I have XY plane. This is quotiented. We have already shown you that this is an ideal, so you can have this quotient. Now my question is how each element of R3 quotient XY plane looks like geometrically. So that's a kind of question that could be asked from algebra, and it will switch from algebra to geometry. Okay. Now tell me somebody. Anybody, please try. Unmute yourself and let me know. Anybody?
Plane parallel to XY plane.
Okay, yes, I get your some of the voices, but from that part it's clear. Okay, so he says that each element should look like a plane which is parallel to xy plane. Is it clear to all of you? Is it clear to all of you? Anybody else? What he told, is it clear? Okay, so let us try to have a look at it. So this is one point, say ABC. Okay. Now, first try to write in a set theoretic notion how this R3 quotient XY plane looks like. Oh, sorry, XY plane. So it looks like an element of R3. So element of R3 means some A, B, C plus the XY plane. If we write it in a set theoretic notation, it looks like XY 0 says that x comma y belongs to R. Okay, so that's the notation for this. So this is kind of R and this is kind of I. So this is R plus I in our notation. Now if I write it in a bigger way, then how it looks like? So all the elements are added with A, B, and C, all the elements. So it should look like A plus X, B plus Y, and C, such that X, Y belongs to R. First of all, see here all the elements should vary. So I must also write here A, B, C belongs to R3. Okay. So if you remember, then the definition was given here such that R belongs to R. That means you need to vary R over the whole ring. So here also I am taking just one point ABC. So this ABC must vary over the whole ring, right? So this is the collection of all such that A, B, C belongs to R3. Now if I consider only one element here, take one element here. So how the one element of this quotient ring looks like? So one element of this should look like R plus I, right? So here also one element of this ring should look like some, say, alpha, beta, gamma plus this xy plane. That means xy0 such that xy belongs to R. Clear? That means it should look like alpha plus x, beta plus y, and gamma such that xy belongs to R, where you can understand that this belongs to R3. Now, what is the geometrical interpretation of this? So this is one element of this quotient. So this is just one element. As I have mentioned, if R quotient I is the ring, then one element should look like R plus I. So here this is my R for a particular R. So here this is my particular R and this is my particular I. So the whole thing is nothing but a set. As in case of, we have already seen, as in case of 4z, this is nothing but one element should looks like this. So one element is nothing but a set. Here also one element is nothing but a set. Now what is the geometrical interpretation of this set in R3? That you can very well understand that here if I have alpha, alpha is a fixed element, x is varying over R. That means it actually varies over whole of R. Similarly, this varies over whole of R, but this is fixed, a fixed gamma. And depending on this gamma, what is you are getting? You are getting basically the dependent for a fixed value of gamma, you are basically getting a plane, xy plane, which passes through gamma and which is parallel to this xy plane. So if your any point is alpha, beta, gamma, then this is nothing but the plane which passes through gamma. So gamma is here. So this coordinate, you can say that this is 0, 0, gamma. So this point passes through this point as well, and this is parallel to xy plane. So this is your xy plane. So one of the element, as mentioned, Shantanu mentioned about that one element looks like an a plane which is parallel to xy plane, because if you vary x and y here, these two coordinate actually basically gives you whole of R. So this is R, this is whole of R, and this is a fixed gamma. That means you are having basically a plane which passes through this point, but it's parallel to xy plane. Is it clear to all of you? Is it clear to all of you? Anybody have any doubt or question? Please ask me. Any question or comments? Anybody, if you have? Is it clear to all of you then? If you
Yes,
have
sir.
any question, okay, good. So I can say I call this kind of things as infinite braid because in real line, so you can consider Z to be a real line. You can take any 2 points in the real line, and as we know from the dense property of R, that between any 2 points there exist again infinitely many points. So for any two planes, any 2 points, you could think of, imagine, or you can have infinitely many planes which passes through this in between points. So I call this kind of structure as infinite braid. Infinite braid. And I call it infinite because it looks like a braid, and in between any two braids, you can always construct a braid. So that's I call it, it's my naming, it's I just call it as infinite braid. And if we have at least one of this infinite braid, then in the whole world we don't have any kind of food problem, because whenever you want, take any two braid and then you can have infinitely many braids you can always generate. Anyway, so the next question is R quotient I, and so is R quotient I uh, an integral domain? Is R quotient I an integral domain? So you have a ring structure here, and you know now this elements you know. Now my question is R quotient I an integral domain? What would be your answer? Is the question clear to you? Okay, is the question clear to you? Is R quotient I an integral domain? Now try to think this question. So it's a homework for you. Or is R quotient I a field? So two of my questions. Okay. So you think. So they are quite interesting to think about, whether R quotient, what it looks like and how it looks like. And then, so you have a ring structure, and then what could be the identity element of this, and what could be all the things that you need to think, and then tell me whether this is an integral domain or not. So this kind of questions are quite tricky, and they are sometimes asked in the very various competitive exams. Okay, now I will go to another interesting ring. Say R is a ring set of all such A by B belongs to Q, that means rational number, such that, say any prime, say 5 does not divide B. So suddenly this is a subset of Q. So we know that Q plus dot is a ring. Also, it's a ring and field with respect to usual addition and multiplication that we all know. Now I consider a subset R, which is of this form. For example, say 1 by 3. Is 1 by 3 belongs to R? Of course R, because 5 does not divide uh, 3. Okay, can you tell me whether, say, 5 by 15 belongs to R or not? Can somebody tell me whether 5 by 15 belongs to R or not?
No, because GCD must be 1.
Sorry?
The greatest compromise is 1.
Okay, I didn't get your voice. Anyway, so it's a good question whether 5 by 15 belongs to R or not? Okay, if I ask you the question, what is a rational number? Can anybody tell me what is a rational number? Okay, Apurvo, can you tell me what is a rational number? Apurvo is here. Okay, let's see. Okay, Provitro.
Yes, sir.
Yes, what is a rational number? Can you tell me?
Uh, P by Q, where uh, P belongs to natural number,
P by
or Q
Q.
belongs P belongs to natural number, Q belongs to Z, or PQ belongs to Z, where GCD of PQ equal to 1.
Okay, so PQ belong, whatever you are telling, I'm writing PQ belongs to Z and GCD
Of PQ equal to 1.
PQ equal to 1. Okay, so that is your definition of a rational number, right? I think many of you will agree with him. Now my question to you is 15 by say 45 a rational number? So what would be your answer? 15 by 45, is it a rational number? Yes.
Actually, each rational numbers represent a class where I can take the relation as R2 in R2 such that A, B and C, D are related such that if A by B equal to C by D.
Okay,
In
good,
this
good
relation,
enough. Okay, yes, I will come to you. Yes, so I will ask you this question. Do you agree with this definition or not?
yes,
You agree with this definition, right? So if I ask you what is a rational number, you will tell me that rational number is of this form P by Q, where PQ belongs to Z and GCD of PQ must be equal to 1. So you agree with this rational number definition or not? Yes or no? Yes or no?
yes,
Yes. So you agree with the definition of a rational number, right? Now my second question is this is a rational number? Yes or no?
it is. It is same as 1 by 3.
No, I am not asking you whether same or not. My question is 15 by 45 is a rational number? Yes or no?
Yes,
Yes, it's a rational number. Again, it violates your definition then, because GCD of 15 and 45 is not 1, right? What now the question that what you told, what you told is perfectly okay. So the definition of rational number should be like this. It's of the form P by Q, where PQ belongs to Z and Q not equal to 0. That is sufficient. Okay. So a rational number is this, where P and Q belongs to Z and Q not equal to 0. Now the question that you raised, that how to get this unique representation, to you for getting this unique representation we should have GCD of PQ equal to 1. So for the definition of rational number this is enough, but to get a unique representation we have this relation as you mentioned. So this is the set of all rational numbers. So here, so every element of this form C by D kind of. Now two elements are related if and only if what you mentioned AD equal to BC. Now you can show that this is an equivalence relation. What does it mean? If we have equivalence relation on a non-empty set, then it must have some partition. So it will break the whole of the rational numbers into disjoint subsets, and each of these subsets basically they are the classes. For example, here I have 15 by 45. At the same time I will also have 1 by 3, so they all belong to the same class. As we represent the quotient leader or the representative of each of these class, so here 1 by 3 you can consider him as a representative. That's why 1 by 15 by 45 is same as 1 by 3. So you now cannot distinguish between them. But to have the set Q, it's sufficient to have this definition. So it's a kind of misconception, or sometimes we do not think, we talk it very lightly, but for algebra, when we are actually dealing with the algebraic structures and algebraic definitions, we need this kind of very particular thing. Okay, is it clear to all of you now? Any question or comments? If you have, you are welcome. Nikita, is it clear now?
Yes, sir.
Good. So what you told is perfectly correct, but definition wise, this is enough. Okay. So now, so here we are actually dealing with, say, Q. Q means if we have, maybe you can think that A and B, they are in a list form. That means they don't have any common factors. Okay. Now, is this R a ring? Can you tell me whether this R, so this R, as I defined earlier, R is of this form, A by B belongs to Q, such that 5 does not divide B. With respect to usual addition and multiplication of rational numbers, is this a ring? What will be your guess? How to show that this is, whether this is a ring or not? What to show and how to show? So what you are going to show then to show that this is a ring? Any guess, any idea?
Basically, subring.
Okay,
I will show this is a subring of.
good. So to show that this is a ring, it's sufficient to show that this is a subring of Q plus dot. So as from the definition, subring means it's itself a ring with respect to plus and dot, but that is in the sense of restriction, because Q is a subset of, sorry, R is a subset of Q. So it's very easy to show that they are a subring of Q. So now it's very easy for you whether this is a subring or not. So at the end of the day, I can say that, of course, if this is a subring, then certainly it must be a ring on his own right. Okay. Now the question is, if I consider another set I, say A by B belongs to R, R means this R, such that 5 divides A. So this is a subset of R, right? So this is a subset of R. Now my question is I an ideal of R? What will be your answer? Okay,
Yes, sir.
on
It will be an ideal.
it will be an ideal. How to
Ideal.
prove that this is an ideal?
So this set I can be rewritten as 5R, 5 capital R.
Okay, just a minute. It's our R and this is my I. Okay, so I'm not going. Yes, what you told is exactly perfectly okay. But if I want to just recap the properties for how to check whether this is an ideal of a ring, the normal way, what would be your approach? What you told is perfectly okay, but what I want to emphasize is just to use the basic tools without knowing the what is the concept of generator and all. I just want to use the basic tools so that I can show you that I is an ideal. Then the idea, as I mentioned, two elements you can take it, say A1 by B1 and A2 by B2. Then suddenly you can very easily check minus A2 by B2 belongs to R. That's very easy to check. Now what you need to check, take an element from R. So how the element of R looks like, some x comma x by y. So what is that property of R? So property of x by y. So here 5 does not divide y. and take any element A by B belongs to, say this belongs to R, and take A by B belongs to I. What is that property? 5 divide A, right? 5 divides A. Now my aim is to basically check what is this into A by B. So this is a commutative ring. R is a subring of Q. So Q is a commutative ring. So R has to be a commutative ring. Now what I need to check is basically this should belongs to I. So that should belongs to I. Now the question is it really happening here? To show that this belongs to I, what I need to show? I need to show basically 5 divides the numerator. So 5 divides x comma a. Now check 5 divides a, right? So you are basically multiplying this by x by y. Now see that within this y there is no component of 5, no component of 5 present here, so there is no chance that that will be getting cancelled. Okay, so suddenly this 5x into a, that must be divisible by 5. So the numerator is divisible by 5. That implies that the whole thing, that means this is an ideal. Firstly, it has to be non-empty. I need to show that this is non-empty. That you can very easily show, because 0 by b belongs to R and 5 divides 0. So I is non-empty. First step is I is non-empty. So second step is to take two elements, then you can subtract them, then you have this property. Take any element from R, so they have this property, and finally the 5 divides the numerator x into a, that implies x by y into a by b belongs to I. So since this is a commutative ring, so it's sufficient to have this as an ideal and both sided ideal. Now my question is, what is R quotient I? So is R quotient I an integral domain? Is R quotient I a field? What is your idea? So you need to check this too. Okay. So any idea whether they are field or they are integral domain or something? If they are filled, then certainly they are integral domain. So the question is, as I just going back to our usual kind of recapitulation of the definitions, I am just giving you some exercise to you to check whether they are integral domain or they are filled or not. Okay. Now I'll go to another important aspect, another important example. So it's again, we have already talked about polynomial ring. That means if R is a ring, then what is Rx? Rx is collection of all such polynomial fx. Fx belongs to fx is a polynomial with coefficients from R. So for example, if I consider zx, then an element should look like 2 plus say 4x plus 5x square. So all this 2, 4 and 5, they belongs to Z, the base ring. Okay, but 2 plus 4 by 3x plus 5 by say 7x square does not belongs to ZX. Why not? Because these two elements are not within Z. But certainly 2 plus 4 by 3x plus 5 by 7x square belongs to R or maybe QX. So, but if I write this 2 plus say square root of 3 by 7x plus say 2x square, then this belongs to Rx because this coefficient is not within Q. But if I write it I plus x, then suddenly this belongs to Cx and so on. So now you have some idea what is a polynomial ring. Polynomial ring means if you have a ring, then take all the polynomials whose coefficient should come from that ring. That's enough. Okay. So we have such examples. Now have a look at a particular kind of ring. Okay. Say R is a ring, say of this form, say all such polynomials belongs to Rx, means real coefficient, such that fx does not have any term with degree 1 or 0. So that means all polynomials with real coefficients, but it does not have any term with degree 1 or 0. That means, for example, fx should look like this, say x squared plus x cube plus maybe root 3 x to the power 6, because it does not have any term of degree 1 or degree 0. Okay, so no constant is here, so constant terms are of degree 0, and 1 degree means no x is there. But if your fx is 1 plus x to the power 7 plus root 7 x to the power 9, then suddenly this does not belongs to R, because this term is of degree 0. So I want all kind of polynomials which does not have any term with degree 1 or degree 0. Okay, now it's clear to your. Now the first question is so suddenly this is a subset of polynomial rings with real coefficients, right? Now the question is R a ring? Is R a ring? What will be your answer? What will be your answer?
Yes.
Yes. Okay. What about rest of the students? Tell me. I heard from other faculty members that your class is not interactive, so that should not be the case. You should interact, please. Okay. So is R a ring?
Yes, sir. R must be a ring.
Okay, then what is the zero element of R? So according to you, R plus dot is a ring. Okay, is a ring. It's your question. Now my question is, what is the zero element? What is the zero element or identity element? Sorry, additive identity. Identity means I want to say additive identity. So what is the additive identity element of R?
Actually, it is polynomial. Fx equals polynomial. By convention, that polynomial has a degree minus infinity.
No, it's depends. It's mostly okay. Let me ask some other guy. Okay, let me ask whom. Uh, to whom shall I? Okay. So Orindam,
Yes, sir.
yes, can you tell me what is the additive identity element?
Actually, sir, I am thinking it. Additive identity must be the one, and this is the degree is
Additive
not.
identity must be the which one?
Uh, additive identity should be the one, zero,
Zero.
and R is defined here that it is not degree one or zero. So
So that's the point. So I just want to point out few of the misconceptions that usually the students they do have. Okay. Anything? Anyone else? Let's say Kailash.
Yes, sir. Yes, sir. I'm thinking.
You are also thinking. Okay, but you believe that R must be a ring, or now you have a question or doubt that R may not be a ring because you have might have some crisis with zero element.
Yes, sir. Now I am starting to doubt it.
Okay. Yes, doubt is good. Okay, Alamgir.
Yes, sir.
So what would be your justification?
So in R, then usually line, but
Not getting you.
zero is
Voice.
the
Zero is the, but is it is zero element belongs to R?
sir. I am thinking so.
You are also thinking. Okay, Nikita, is the zero element belongs to R?
No, sir. Mm,
Why
I'm
not?
thinking.
You are also thinking. Okay, so the basic concept here is what is the degree of zero polynomial? Okay, degree of zero polynomial. So zero polynomial, you are trying to guess that zero polynomial could be the zero element of R, right? So what is the degree of zero polynomial? So remember, the degree of zero polynomial is not zero. Okay, so it's basically not defined. So we usually do not define the degree of a polynomial in which the degree of the polynomial is the zero polynomial. That means if fx equal to 0, then we degree is defined for non-zero polynomials. It may be a constant polynomial. That means if it is 1 instead of 1 or anything r where r not equal to 0, then if it's a constant term, then the degree will be 0. So in case of zero polynomial, there is no degree. That's why here it says that it does not have any constant term other than 0. And degree 1 is fine with you, no problem. So 0 is very much there because there is nothing to deal with degree 0. Okay, so the additive identity is the zero polynomial. Now who is the multiplicative identity element? That means who is the identity of 1R? Is who is that guy? Okay, who will tell? Maybe Pavitro.
Sir, thinking.
For multiplicative identity.
Yes, sir.
Oh, that's not good. You should tell what is multiplicative identity. That's easy. Okay, Shilpa. What would be the multiplicative identity?
Sir, I'm thinking.
So usually what element should be? For Rx, what is the multiplicative identity? For Rx,
One.
1. So what is the degree of 1? Polynomial 1?
Sir, zero.
Degree of this is 0. So now you can understand that 0 is not here. That means 1 is not an element of R. So anything, any other polynomial, if you multiply with some other polynomial other than 1, is there any chance of getting back that polynomial? Because here it's R. So R is a field. So,
No, sir.
so no. So that means R is a ring without multiplicative identity, right? Is it clear to you now? Okay. Now, suppose I am considering an ideal of it, maybe. Okay, can you tell me any ideal of it? Any ideal of this ring? Any ideal of this ring? Can you tell me? Any ideal of this ring? Okay, is this very difficult question? It's easy. Any ideal of this ring? So 0 is an ideal. So if you consider
Because
0,
it
any non-trivial ideal of it?
Sir, ideal generated by X.
Ideal generated by X. Okay. So if I consider ideal generated by X, let's see. Can you tell me how it looks like? Ideal generated by X.
It looks like XFX, XHX, where HX belongs to RX.
Okay. So somebody says ideal generated by X, right? So it should look like. So this element should belongs to where? This X. X should
Oh, sorry,
belongs
sir.
to. So
Sorry,
now
X
you
doesn't.
understand. So
So X
X
square,
is,
ideal generated by X square.
yes, good. So X does not belongs to R. See, because R should contain the elements 0 element and then all the elements starting from degree 2 and onwards. So X is not element, but ideal generated by X square is an element of this. So some of you might not heard about what is the ideal generated by this. So we may talk about what is ideal generated by this. So uh, I will discuss what is the ideal generated by this. Now, if I ask you the question, what is, say, Rx quotient R? So if I have, so what I have seen that this is a subring, right? And so this is itself a ring. Now my question is is R, is R an ideal of Rx? Is R an ideal of Rx? So in
Yes,
R,
sir.
we have seen that this is a subring. Now my question is R an ideal of Rx? That you can very easily check. That take any two ideals. First of all, it's a non-empty. Certainly zero element belongs to small this R. So this is certainly non-empty. And then take any two elements from R. Then if you subtract them, suddenly it will not contain any degree 1 or degree 1 term, 0 term. So this is done. And if you multiply with any polynomial with this, for example, for the sake of simplicity, if I take fx equal to any polynomial from Rx, say a0 plus a1x plus a2x square, and if you multiply with any element from R, say R may be an element like this, x, say a3x cube plus a4 x to the power 4, then if you multiply this by this is just an example. I am not giving you the formal proof. This is just to show you. So if you just multiply with them, then you can understand that all these coefficients, they will not be there in the product term, fx into gx, not in the, I mean, constant term. So here if you multiply with this, so you can understand that from here you have x3 in common, so a0 plus a4x. Now if you multiply this with f, then this a0 becomes a0 x's cube and so on. So in this product term, there will be no degree 1 or degree 0 term. So now you can understand that R is an ideal of R. Is it clear to all of you? So it's a commutative ring. So it's sufficient to have a look from left. Then we are done basically. Is the idea clear that R is an ideal of Rx? Clear? Any doubt to anybody? Please let me know. Okay. So if this idea is clear, then the certain question, as I asked earlier, that what is Rx quotient R? So again, the same question is Rx quotient R and integral domain and field. So again, you need to think about it and you need to answer. So they are very interesting question that one may ask. Is the question clear to all of you? So it's not very difficult to see what would be the answer. Okay. Now now let me very quickly go to some applications of number theory using this quotient group. Okay. So I ask you a very simple question. Find all integral solution of the equation, say x square plus y square equal to 3z square. So find all integral solutions of the equation x square plus y square equal to 3z square. That means all such I need to find. So I need to find x, y, z belongs to z such that x square plus y square equal to 3z square is satisfied. Okay, can anybody tell me quickly? Okay, first give me any integral solution, at least one solution of it. Quickly, one solution.
So 0, 0, 0.
Very good. So it must have at least one solution, 0, 0, 0. So now let us try to find some non-zero solution. So now try to find some non-zero solution. Non-zero integral solution means I need to find x, y, z belongs to z3 such that x, y, z is not equal to 0, 0, 0. That means you may have some of the terms 0 and some of the terms non-zero. Can you find such? Okay, so that's my question. So what would be your guess? Can you give me quickly any other solution of this equation? Try. Okay, so let us try to use here the idea of quotient ring here. So basically we are considering here the solutions from Z. So we know that Z plus dot is a ring. Now we shift the whole question from this ring into a quotient ring. So I should have some proper quotient ring which is obtained from here. Suppose I consider the whole question in this quotient ring. So we know that this is a quotient ring because 4z is an ideal. So this is a quotient ring with respect to the proper addition and multiplication. Now, if I ask the same question instead of z, if I ask the same question here, okay, then the question would be what? So here the elements are coming from z. Now the elements will come from this. Okay, so as I mentioned, this is, I suppose for the simplicity I call it so we understand that this is isomorphic to Z4. I'm sure that you all know, or okay, let me instead of this I will write like this itself. So now I shift the question, is there elements, is there exist, is there any, okay, are there, it should be are there exist elements x plus z 4z y plus z 4z and z plus z 4z such that x plus z 4z whole square plus y plus z 4z whole square equal to z plus z 4z, sorry, 4z whole square. Okay, so it looks quite weird to you. You may not understand why I am writing this, but let me do it for a uh, general ring, then it will be clear to all of you. Suppose some relation is satisfied here, say A equal to B, where A and B are from a ring, and say I be an ideal. Then A equal to B suddenly imply A plus I equal to B plus I. And is the converse true? First of all, is it true? If A equal to B, then will A plus I equal to B plus I? Is it true? What will be your answer? Yes or no? Please tell me, somebody. Is it true? If A equal to B, then A plus I should be equal to B plus I. Is it true?
Yes, yes.
Yes.
Yes, sir.
Very good. So the answer is yes. Very correct. But if A plus I equal to B plus I, will it imply A equal to B? Yes or no? What would be your answer?
No, sir.
Oh, sir.
So it may not be. For example, as we have seen, 0 plus 4z equal to 4 plus 4z, right? So this is the justification. That does not mean 0 equal to 4 in z, right? So it's not true. The answer is basically true. What in that sense it's true that a plus b equal to, sorry, a plus I equal to b plus I if and only if a minus b belongs to I. It's not like a equal to b, and this is an if and only if condition that you all have done in your undergraduate level. Okay, so this part is always correct. So if this happens, then the same relation may be translated in the quotient ring. The same relation, but in the quotient ring, the corresponding element here and this is the corresponding element here, the same relation holds. So as a result, when I talked about if this relation holds, so suppose this is an element and this is an element, two elements in Z, then my question is, as I mentioned now, I am now posing the same question but in the quotient field or quotient ring. Now it's not field, in the quotient ring. So the similar answer will be just a addition of this. That means x square plus y square plus z quotient 4z must be equal to 3z square plus z quotient 4z. If this is true, if this is satisfied, then this relation must also satisfied. That means if I break it like this as the rule I mentioned, so this should be x square plus z quotient 4z plus y square plus z quotient 4z must be equal to 3z square plus z quotient 4z, right? Oh, so it must be, I did some wrong here. It should be 3z square. Here 3 should come here. Okay, so that means, so as you know that this is nothing but 4z whole square plus y plus z quotient 4z whole square, and that is nothing but 3z plus z quotient 4z whole square. Okay, that what I wrote it here. Okay, so now I come to my original problem. What it says, okay, let me come here. So what it says, whether, so solve x square plus y square equal to 3z square in z plus dot, in the ring z plus dot. That was my original question. Solve in this means all the solutions should be integral. That means they should be integer. Now we have checked already that 0, 0, 0 is a solution. So there exists some solution here. Now my claim is there exists no non-zero solution, integral solution, non-zero integral solution. That means there exists no x, y, z belongs to z cube such that x, y, z not equal to 0, 0, 0. That means you cannot find any xyz such that xyz are non-zero. Okay, that is my claim. I need to prove it. So if possible, as I mentioned, it's a very old technique. Euclid in more than 3000 years back, he used the method of contradiction. So if possible, let there exist some integral solution Non-zero integral. There exists some non-zero integral solution, say ABC. Okay, so not all ABCs are zero. So you can see that from here, without loss of generality, you can assume that there exist no common factors among this ABC. So if there are some common factors, you can always make a common of this, and you can just make a cancellation of this. So ultimately, you can assume that without loss of generality, we may assume that A, B, C have no common factor, non-trivial common factor, no non-trivial. One is always a common factor, non-trivial common factor. Okay. Now, I now pose the same problem. So now my solution exists. So that is ABC. Then this relation must hold from here because ABC is a solution. So A square plus B square equal to 3C square. Okay. Now I pose the same problem. So this relation holds. Now we come to just shift the question from here to its quotient ring. Consider the quotient ring Z quotient 4Z. Then, as I mentioned earlier, if this are equal in the ring, then it must be equal in the quotient ring as well. Then I must have A square plus Z 4Z plus B square plus Z 4Z equal to 3 C square plus Z 4Z. Okay. Now have a look at this elements ABC. So ABC may be any integer, right? Not all ABCs are zero. Okay. Uh, so here, what is the values of ABC, right? If I consider this set, what could be the values of A square plus Z quotient 4Z? Say if A is 0, then its values become A square plus 4Z quotient 4Z, its values becomes 0 plus Z quotient 4Z. If the A is 1, then its values will be 1 plus 1 square is 1, that means Z plus 4Z. If the value of A is 2, if it is 2, then what would be this value? 2 square means 4. 4 plus Z plus 4Z, as I mentioned, this is nothing but 0 plus Z quotient 4Z. And if its value is 3, then its value becomes 9. 9 plus Z plus 4Z, same as 1 plus Z plus 4Z. Okay. If this value is 4, then it becomes 0 plus Z quotient 4Z and so on. So what we observe that whatever be the values 0, 1, 2, 3, 4, whatever integer it may be, its value is either 0 plus Z quotient 4Z or 1 plus Z quotient 4Z. So other than these two values, this square value will not take any value. Similarly for B square, similarly for 3C square. In case of 3C square, this value could be either 0 plus Z quotient 4Z or 3 plus Z quotient 4Z. So from equation 1, if I take all the possible values, then we can see that though A varies over all Z, it ultimately gives you two values. Either this could be 0 plus Z quotient 4Z this a square value, note that this a square value, or this could be 1 plus z quotient 4z. So this could be one value, set of values of this, plus 0 plus z quotient 4z, or 1 plus z quotient 4z, equal to, these values will be either 0 plus z quotient 4z or 3 plus z quotient 4z. Now from this equation, tell me that what could be the values of this a square, b square and c square. What could be the only possibility here, so that this plus, so if I take this one and this one, then the answer should be 1, which is not here. That means these values cannot be taken simultaneously. If you have this and this, then also the addition will be 1, which is not here. So there are all, if you consider all possible solutions here, then you can find that 0, 0, 0 are the only solutions. That means you can only have, among this, you can only have the values of a, b and c must be, tell me what should be the relation, must be in terms of z, in terms of, give me some property which will actually ensure you that it should be 0, it should be 0, and this should also be 0. So that is the only possibility to maintain this equation. Then what should be the values of a, b and c? Tell me what could be the values of a, b and c to maintain this. Somebody tell me. Anybody? Anybody?
Sir, class 0.
Sorry? ABC must be,
Class of 0.
ABC must be 0 in Z.
Class of 0.
Class of 0 in Z means class of 0 in Z. What I am talking about, I need some property of ABC that should be reflected in Z. That means in terms of some integer. Say it may be multiple of 4, it may be multiple of 2, it may be multiple of 3, that way. I have given you the hints. Now tell me, multiple of, could you
2.
repeat? 2.
So multiple
Yes.
of 4.
Yes.
Okay, somebody says it's a multiple of 4. Anything? Some better approximation can be done.
It's multiple of
Multiple, yes. So if it's a multiple, must be a multiple of, must be a multiple of 2, because you are making it a square, right? So this relation is basically for a square. This is b square and this is c square, right? So if must be a multiple of 2, multiple of 4 is also fine, but multiple of 2 is more appropriate, because if it is a multiple of 2, then this square is basically multiple of 4. Multiple of 4 becomes 0, multiple of 4 becomes 0. So a, b, c, all of them must be a multiple of 2. Clear? Now it's okay. Now tell me, what is the contradiction here? That implies a contradiction. Now tell me, what is the contradiction?
So we have assumed that ABC has no common factor.
Exactly. As assumed that A, B, C have no common factor. So We are done basically. So we assume that there exists some non-zero solution, but we again get a contradiction. So we are done. So now you can understand that the application of number theory can be now done using this ring theory. So they are very much related. And as I mentioned in my last class, while the ring theory evolved, one of the reasons for evolving this commutative ring theory was to solve this kind of equation. And this kind of equations are known as diophantine equation. So diophantine equation, so Fermat's last theorem, as I mentioned, that is again dealing with a diophantine equation. So how to solve this kind of, or how many solutions are there in integral solutions are there? To answer these questions, many of the ring theoretic techniques or many of the ring theoretic development came into picture. So that's why number theory and ring theory are very much connected, and number theory may be considered as the one of the origins for commutative ring theory. Okay, so what we started with a ring, then we make it at quotient, and somehow we show that some properties, some relations will not be happening in R by using the properties of this. But I have used here is a particular, so for Z, right? But this technique may not be done always. Okay, I will giving you some example. Suppose my question is find all integral solution of x square plus y square plus z square plus say w square equal to -1. Can you tell me any x, y, z, w which satisfies this? Of course, integral means integer. Any x, y, z, w which are integers which satisfy this equation? Quick, anybody?
So no solution.
So no integral solution. Okay. So there exists no integral solution. Now I try to use this concept in case of the quotient ring. Well, so suppose I take any n greater than 1, take any n greater than 1. Okay. Then the same question may be asked here also. X square plus y square plus z square plus w square plus z quotient nz equal to minus n plus z quotient, sorry, -1. So it should be -1. Okay, I'm writing it. So -1 plus z quotient nz. Okay. Now you can very well write it like n minus 1 plus z quotient nz. So they are same, because if you take the difference, that will be the zero element, right? Now if you see that, if you, I think in number theory classes you must have or might have heard about that any positive integer can be written as sum of 4 squares, and it has very interesting proof, very historical proofs. I am not going to, in the number theory class I might have done this. So so it's a very interesting fact. Any positive integer, take any positive integer, say 4, then you can see that it can be written as 2 square plus 0 square plus 0 square plus 0 square. Take say 5, you can see that 2 square plus 1 square plus 0 square plus 0 square, and so on. So it can be proved, and there is a very simple proof of this. So if you consider this, then n minus 1, since n is greater than 1, so this is a positive integer. So you can understand that for this positive integer n plus 1, there exists x, y, z, w which are integer, which can be written like this, and then you can convert it. So for this equation you have solution, but this solution will not satisfy this equation, because what is happening here, like a plus I equal to b plus I is correct. That means I can, for this n minus 1, I can always find x, y, z, w plus this, such that their square must be equal to n minus 1 plus this. That means this equation is satisfied. That does not mean that a equal to b. If a equal to b, if that will imply a equal to b, then from there I can directly say that this, because our original equation was this, where it was minus 1, but now in case of a class I have converted minus 1 into n minus 1, and for n minus 1 there are solutions. So this relation is satisfied, but that does not mean that a equal to b. As a result, you can see that for any positive integer n greater than 1, this relation is satisfied. But from here, you cannot conclude that this equal to minus 1, that is satisfied with that particular x, y, z, w in case of this. Is it clear to all of you? So in 4z, we were fortunate enough in our last example that we were unable to find any non-zero x, y, z. That's why our conclusion is satisfied. But here we are getting a solution. As a result, we cannot directly convert into the back direction to go back to R. So from R quotient I cannot go back to R. But the converse is true. So from R I can directly go back to R quotient I. But from R quotient I cannot conclude anything regarding this equation. So is it clear to all of you? So we have to be very careful while dealing with positive comments or negative comments. So it's a contrapositive way, but we have to be very logically very much clear. Otherwise, sometimes in case of some competitive exam, when you may not have much time, so if you think in a very light way, sometimes you may be misleaded, and that will reduce your marks. And most of the cases, that's actually happening for competitive exams. Okay. Now, for the last thing that I'm going to do, it's is basically the basic idea of homomorphism. Okay. So in case of, I'm sure that in your undergraduate level, you have all done this homomorphism for group. Say, for example, suppose G is a group, say with respect to star, and say H is another group with respect to, say, composition. So when I call this is a homomorphism, so A star B must be equal to FA composition FB. So if I write it like this, so this is my F, this is my G, this is my H. So take two elements, any two elements, then from the definition of group, their binary operation on A and B must also be in G. Now take F. So F is a function. So with take F here. So FA must be an element here. FB must be an element here. If A star B must be an element here, because it will send A, B and A star B into H. Now, since FA and FB, they are in H, so their composition, FA composition FB, must be here from the definition of the group. Now, if it happens that these are equal, see, I find it directly from here, and I had FA and FB at my hand, and I had a composition. If it happens like FA composition FB is always equal to FA star FB, and not only for only say few AB, but it should be true for all AB belongs to G, then we call it as a homomorphism. So I think this concept is very much clear, and in abstract algebra, homomorphism plays a very important role. Okay. So if you forget about it, do not, repent. Just go back to any of the books, either Damit Food or my book or the Malik Shen Moderation or any other book that you already studied with. Then just have a look at the definition and few examples. That will give you some confidence about homomorphism and all. Now, if this homomorphism, along with this homomorphism, so it's a function. If this is injective and homomorphism, then we call it monomorphism. If it is surjective and homomorphism, we call it epimorphism. And if it is bijective and homomorphism, then we call it isomorphism. So we all know. And for algebraists, this isomorphism plays an important role. So I may give you a few examples. For example, if I consider Z2 cross Z2 and Klein's 4 group, they looks completely different because here you elements looks like AB such that A belongs to Z2, B belongs to Z2, and here the elements look like E, A, B and C, and you have a kind of table. Here also you can have a table. So you can see that this is a kind of additive group, but here the composition may be like this where composition is defined here. But apparently they look quite different, but they have the exact same algebraic property. That's why both the groups are same. So there are many common things are there. So in the as an exercise, I just want to mention few of them. Say for example, I'll just okay. I'll, okay, maybe here I'll just okay, few more examples. What I'm not giving you the hints, but you need to do that. They are very important for competitive exams. The groups like Q quotient Z. I talked many thing about quotients. Then R quotient Z and C quotient Z. Okay. Then I'm considering another group, say S1. You know what is S1? What is S1? S1 is basically geometrically you can think of is a unit circle, all points on the unit circle. That means all such Z belongs to C such that mod Z equal to 1. I am again considering another group of units, say U. I consider all such Z belongs to C complex number such that j to the power n equal to 1, and this n varies over 0, 1, 2 and so on. That means all group of units, nth root of units where n varies. And I am again considering another group C star, that means complex number C and removing the 0 element and then with respect to multiplication. So you can see that all of them, so they are subsets of C star, they are subset of, sorry, they are subset, it's not belongs to, so they are subset of C star, that is also a subset of C star, and of course this is C star equal to C star. So all of them, they are basically in a complex plane, but here you have this. Now can you tell me which of the pairs are isomorphic as group? So the proving of this is not very easy. Okay, so you have to go through little bit more, then you will able to understand that there are pairs. Say I can say 1, 2, say 3, that 4, 5 and 6. Now it will be your turn to tell me, maybe in the next class or maybe at your some homework or some tutorial classes, that there are pairs which are isomorphic. Okay, apparently they are quite different, but all these groups, they do have lots of interesting properties, and this group, believe me, these groups are very important for all the interviews for institutes. So many questions are asked from this groups. Okay. Another thing, you might have be very surprised to know that this C, right? The complex numbers, say the ring of complex numbers. And in my earlier class, I have already mentioned about M2R. So this is 2 by 2 matrices over R. Now, the algebraists, so they are completely different in an apparent. So it's a complex numbers and they are matrices. It's a very much, you can think they are very much pretty from real linear algebra, very much algebraic structures. And here they are from complex analysis, or in a bigger sense, maybe some relation with maybe real analysis and all. But you will be surprised to know that within this M2R, this as a subring C is there. So they look quite different. But algebraically, we can say that C may be thought of as something called embedding. So C is embedded within M2R. And here the this homomorphism, isomorphism, these things plays an important role. So homomorphism, endomorphism, or epimorphism, they are playing an important role. So these things are very important in case of our algebraic structures. Okay, so I think I can stop here today. So if you have any question or comments, you can ask me. This is left as an exercise in your group class. You might have done this or you will do this, but they are very important for all the competitive exams, and this is also quite interesting. So any questions that you have, you can ask me.